Okay, guys, so look, something came up. I had to make a recording of this, what I planned on going over with you here on today, Tuesday, for the part one of 3 ionic review sessions. So ionic compounds, all right, always are going to be between our friends, the metals, right, which is the left-hand side of the periodic table, and the non-metals, all right, the right-hand side of the periodic table. And what you need to understand is with an ionic compound, you're always going to have metals, which tends to have, and remember, if I'm in the first column, I have 1 valence electron. If I'm in the second column, column number 2, I have 2 valence electrons. We'll talk about the transition metals either today or a little bit later on. If, when we get over here, column 13, all right, I'm going to have 3 valence electrons, 14, 4 valence electrons, 15, 5 valence electrons. So where I am in the periodic table tells me how many valence electrons I have. That's key, all right? Metals tend to have small numbers of valence electrons, 1, 2, right? Everybody wants to get to 8. Everyone wants to have a full octet. And so in order to have a full octet, the metals will easily give up their 1 or 2 valence electrons. Whereas the nonmetals, with their perhaps 5 or 6 or 7, they're going to tend to gain electrons. Because if I'm sitting here, if I'm fluorine and I'm sitting here at 7 valence electrons, if I can just convince somebody to give me 1 extra electron, now I've gone from having 7 valence electrons to having 8 valence electrons, and now I feel like a noble gas. So that's just quickie sort of background about why metals give up electrons and nonmetals take the electrons. Now, what I want to do is, because this shows up on the quiz, and I think some of you got thrown off by this, I'm going to hopefully switch up my camera. So let me pause this and switch the cameras. So now let's go ahead and start talking about some make-believe ionic compounds. Let's say that I wanted to take some bobium, all right, and combine it with some biogen, all right. So bobium is over here, and I'm going to go ahead and scoot this down a little bit. Bobium is in column number 2. So one of the questions that I ask you to think about on that quiz is to draw a Lewis dot structure, all right. Bobium has 2 valence electrons. So what I'm going to do is I'm going to put 2 dots on the outside of bobium. Biogen is over here in column 16. So biogen is going to have 6 valence electrons. So you always start and work your way around clockwise, and then you double them up until you get to the number of valence electrons you're supposed to have. So this would be the Lewis dot structure for biogen by itself, and this would be for bobium. 2 valence electrons, 6 valence electrons. Now the reason I chose these is because, let's face it, biogen would be thrilled if this bobium would just give up 1 electron to go there and 1 electron to go there. In doing so, the bobium would no longer have 2 valence electrons, but in losing 2 electrons, the bobium now is going to be +2. Likewise, the biogen, and I've lost my valence electrons, okay? That's why I have no more dots around the outside of it, but I put the +2 because it's an ion, all right? It has a charge, and I need to be mindful of that. The biogen does have a completely full valence shell, so we're going to go ahead and show that all 8 of those are there. And because it now has a charge itself, and we want to make sure that we know who has the valence electrons here, I want to put some brackets, and because it gained 2 electrons, it would have a charge of -2. Now here's the biggie behind understanding writing the names and formulas for ionic compounds. A +2 and a -2. This was a match made in heaven. These 2 electrons found a perfect home right over here. So there is no need for additional bobium atoms or additional biogen atoms. And so this would be what we call the Lewis dot structure for this particular ionic compound, all right? And I know that it's good because it's balanced charge-wise. A +2 and a -2 balances out to 0 overall charge. And that's what you're going to want to have in any ionic compound. All right. So this would be the Lewis dot structure. And then we could take it a step further. I could go ahead and write the actual chemical formula as one of the BOs is going to combine with one of the BYs to form this particular compound. Now, I'll do an entire separate video on naming and writing formulas, but just because we're here, we would want to understand that this would be called bobium. You always take the first element, the metal, and you just write the element name. And then what you're going to do, right? And you can kind of think about this guy. This is an awful lot like oxygen, right? It's in column 16. It's in the second row. And so if this were like oxygen, we would go with oxide. Since it's biogen, we're going to go with biogide, all right? Now, the key here, and this is a make-believe, okay? But the reality is I want all of you to understand that ionic compounds and molecular compounds, so compounds in general, are going to end in IDE, okay? Now, there's some other naming things that we'll go over, but today's emphasis is going to be on the Lewis dot structures. All right, so let's pick one that doesn't work out so nice and neat, all right? Bobium was +2, biogen was -2, easy peasy. Let's go with platium and Addis. All right, so let's go ahead and look and see what that would look like for us. Platium and Addis. So platium is going to have how many valence electrons? It's in column number 1. Hopefully you're okay with 1 valence electron. Addis is in column number 5. And so I'm going to put 5 valence electrons on it. And so you're going to look at this. Platium is the metal, Addis is the non-metal, all right? And at this point you say, okay, well, if I have 1 platium, that would fill 1 hole, okay? But I've still got 2 more places because at the end of the day, Addis wants to have 8. So the only way that this works is to think about another platium, excuse me, coming in here and donating an electron to fill that slot, and a 3rd platium coming in and filling that spot. So at the end of the day, in order for this to work, I would have to have platium, and each one of them is losing an electron, so it becomes a +1 ion. But I need to make an acknowledgement of the fact that there are 3 of them. So I'm going to put a big fat 3 here. And again, this is the Lewis dot structure for this particular combination of elements. And even though I'm making using the make-believe periodic table, this would work the exact same as if I was working with the real periodic table. Note that this is just jumping between column 2 and column 13 because we've eliminated all of the transition metals. So 3 platium ions are going to come together, and this Addis is now going to be so happy with itself. It went from having 5 valence electrons to now having 8. And because it went from neutral to now having 1, 2, 3 additional electrons, it's going to have a charge of -3. And so at the end of the day, this would be the Lewis dot structure, right? 3 platium ions combining with 1 Addis ion. And if I wanted to write the actual formula for this, we just write it as Pl3AT, and the name of this would be, again, platium, because you just take the name of the metal. And instead of it being Addis, it would be attide. Right? You drop the ending on the element, and it becomes IDE. All right. Let's do 1 more of these. And again, I had to do 3 of these because if we look at this charge-wise, 3 +1s, +1, +1, +1 is going to balance out a -3 and again, give me that magical 0 charge that we're always going to be looking for in an ionic compound. All right, let's do 1 more here, all right? And I'm going to go ahead and choose sort of the most challenging of them. Let me go ahead and go with a helium, right? which is sitting here, and I'll scoot this up just a little bit. Helium is sitting here in column 13, which means it has 3 valence electrons. And we're going to go ahead and combine it with, let's say, Pilfer. Pilfer is in column 16, which means that it is going to have 6 valence electrons. So Pi on this, 6 valence electrons, 1, 2, 3, 4, 5, 6. And you look at this for a moment and you realize, oh, it's a little tough because I've got 3 to get rid of here. So I can get rid of 2 real nice and easy. But now I've got 1 more to get rid of. So I need another Pilfer. So let me scoot this down just a little bit. So I'm going to come up with another Pilfer. So again, I draw my 1, 2, 3, 4, and it's supposed to have 6, 5, 6, and oh, well, that gets rid of my 1. But I've got an empty hole here on this Pilfer. So I've got to come up with another helium atom. So again, helium has 3 valence electrons. So I can be like, okay, well, I can go ahead and get rid of this guy. Boop. And now the Pilfer is good, but I've got 2 electrons left over from the helium. So I gotta keep going. I've got to find a home for those helium electrons, and so I've got to have another Pilfer atom. 1, 2, 3, 4, 5, 6. And lo and behold, at long last, I've found a home for every electron. So at the end of the day, look at what we have. We had 2 helium ions. So again, this is the Lewis dot structure, 2 helium ions. And those heliums, each of them lost 3 electrons. So because I lost 3 electrons, I'm going to be plus 3. And it came together with 3 Pilfers. 3. And again, you put all of the, I think my computer screen just died. Hopefully it's still recording okay. So I put all of my electrons around the Pilfer, and because Pilfer gained 2 electrons, each one of them gained 2 electrons, each of the Pilfers is a -2 charge. This would be the Lewis dot structure for this particular ionic compound. And I know that it's right because at the end of the day, a +3 and a +3, because there are 2 of them, is going to cancel out a -2, a -2, and a -2. 3 -2s cancels out 2 +3s. That all combines to give you the magic balance of 0. So writing the final formula for this critter, and again, just so you can see it, here's the helium and here's the Pilfer. We would go ahead and write that this is El, and there are 2 of them, and this would be Pi, and there are 3 of them. And so I would call this helium pilfide. You drop the ending and you put IDE. So this would be helium pilfide. Okay. And so that is a quick run through of Lewis dot structures. Now what I'd like to work on real fast with you is sort of the introduction of writing formulas and names. All right. So now that we've got a little bit of a feel for the Lewis dot structure, all right, understand this. If I'm in column number 1, I'm always going to have 1 valence electron, which means I'm going to always give up that 1 valence electron in an ionic compound, and I'm always going to be a +1 charge if I'm in this column, column number 1. Likewise, if I'm in column number 2, I have 2 valence electrons, so I'm going to give up 2 electrons in an ionic compound, which means if I'm in this column, my charge is going to be +2. If I am a metal in column number 3, I'm going to have 3 valence electrons to give up, so I'll be +3. Let's work our way from the other side, all right? Noble gases for ionic compounds, we don't care about them. They're not going to be reacting. But these guys certainly are important. They have 7 valence electrons, so they're going to gain 1 electron in their reactions. So if I gain an electron, I'll be -1. If I have 6 valence electrons, I need to gain 2 electrons to get to my magic number of 8. And if I have 15, I will have to need 3 electrons. So that helps you remember what charge goes with what element. Depending on which column you're in, that's going to tell you the charge. Now let's just say that we want to combine, we'll go ahead and look at oxium and cation. Right? So let's go ahead and talk about some combinations. So the metal oxium and the non-metal cation. So if I wanted to go ahead and figure out what the formula for this is, I'm going to say, well, oxium we know is going to be, I'm going to put the +1 down here just for sort of safekeeping, and the cation is going to be a -1. And based on what I just talked about with the Lewis dot structures, in that we want to have charges balanced, right? The oxium has one valence electron to give up. It wants 1 electron, so this is a perfect match. So I don't have to write anything else. The formula for this is literally just OXKT. I don't have to write a 1 down here. In fact, nobody does that in chemistry. So this would be OXKT is the formula. The name of this would be called oxium kit. And remember the ending change. The INE is going to change to ide. So this would be called oxium kitide. All right? Let's try another one here. Let's look at neodymium, which is right here, and allyne. Same deal, guys. The neodymium is going to be +1. The allyne is going to be -1. And so a +1 and a -1, brilliant. And so what would we call this? We'd call it neodymium allyde. Now, it starts to get a little bit trickier when we have charges that aren't quite balanced out. All right, let's go ahead and look at, let's take wobium, right? WO, which is sitting here in the column that has 2 valence electrons, so it would be at a +2, and let's combine it with our friend cation, which is sitting at a -1 charge. +2, -1, not balanced. So I'm going to need to balance this out. And how do I balance this out? If I have 2 -1s, that's going to balance out the +2. So that's how I know to indicate that there should be 2 cations in this formula. So what would I write for the name of this? Well, it's wobium kitide. Done and done. All right. Let's go ahead and do one more. All right. Let's say that we are talking about our friend testium. Testium is going to be sitting there with a charge of +3. And let's go ahead and look at pilfer. Pilfer is sitting there with a charge of -2. Well, that won't do. +3 and -2. So I have to look at ways to get both of these positive numbers and negative numbers to the same thing so they cancel each other out. Well, if I have 2 +3s and I have 3 -2s, so for clarity's sake, let me move this over. If I go with T2, Pi3, that's going to give me a +6 and a -6, and I'm sitting there happy dappy at 0. And so the name of this thing would be testium pilfide. All right, so that's the basics of writing formulas. And I think what I'm going to do is pause for today. All right, you've had a long first day back, but hopefully this gives you a little bit of an insight into some of this ionic compound stuff. And we'll have some more videos and learning for you available tomorrow and Thursday after school. All right, guys, thanks, and I'll see you soon. Bye-bye.